A piston cylinder assembly contains 20 kilograms of H2O at 1.2 megapascals. Initially, 16 kilograms is in the liquid form and the rest is vapor. The cylinder is heated at a constant pressure until the temperature reaches 250 degrees Celsius. How much heat was added and how much boundary work did the piston produce? Remember to solve this problem yourself before watching the solution up next. This is the first example for the enthalpy and internal energy 12-minute lecture video. The links to the other examples on this topic and the other lectures of the Thermodynamics course are found in the description below. Using the conservation of energy equation, we can assume that the changes in potential energy and kinetic energy are negligible. We see that the change in internal energy is equal to heat minus work. What we learned in the main lecture video, link below, is that the heat for a constant pressure process is the change in internal energy plus the boundary work, or what is the same, that the heat is equal to the change in enthalpy. This can be m times the change in specific enthalpy. We'll use this to calculate the heat. As for work, we can either calculate delta U with specific internal energy values U1 and U2 and subtract it from the heat, or instead we can calculate it as P V2 minus V1, since this is a constant pressure process. Since we'll be looking for values in the tables anyways to look for specific enthalpy, we'll just use this first approach here. Initially, we have a saturated mixture at 1.2 megapascals. This can only happen if the temperature is the saturation temperature, which is 187.96. Then at state 2, which is still at 1.2 megapascals, but now at 250 Celsius, we know that our water has to be superheated. This all means that for state 1, we need to first calculate the quality, so that with HF and HG and UF and UG, we can calculate H1 and U1. It also means that for state 2, we only need to use the superheated tables to find H2 and U2. The quality is by definition the mass of vapor over the total mass. If 16 kilograms is liquid, then 4 kilograms is vapor, and therefore X is 4 over 20 or 0.2. To calculate the specific enthalpy at state 1, we look up HF, which is 798.33, and HFG, which is the difference between Hg and Hf. Remember that? This is the first time we're using those values. We write down 1985.4 for HFG, and with these values we calculate the specific enthalpy to be 1195.41 for state 1. As for the specific internal energy, we find that UF is 796 and UFG is 1790. This allows us to calculate the specific internal energy of state 1 to be 1155.14. Now, by looking at the superheated tables, we find the one for a pressure of 1.2 megapascals and within it, the row for 250 Celsius. The specific enthalpy is 2935.6 and the specific internal energy is 2704.7. We substitute the specific enthalpy values H1 and H2 in the heat expression from the beginning to find that the total heat that was added to the piston cylinder system was 34.8 megajoules. We substitute the specific internal energy values U1 and U2 to find that the change in internal energy is 31 megajoules and therefore the work is the heat minus this value. The work is equal to 3.81 megajoules. If you want to check out the other more complex examples for this same topic, the main lecture video or other lectures of the Thermodynamics course and other engineering courses, make sure to check out the links in the description below. Thanks for watching.